Okay, so RGB research at SPoRT. So going back to 2012, there was an early application of training and development of RGBs with MODIS and VIIRS to prepare users for GOES-R. So we worked with some of the CONUS forecast offices, heavily with the satellite liaisons, and with Alaska region. And out of that work came limb correction and intercalibration of polar satellites, because we had the air mass RGB from Terra and Aqua. They look different because of some of the different aging of the sensors and spectral characteristics. We worked heavily with some of the southwestern US offices with the dust RGB, where they were well prepared. They were asking for the GOES-16 dust RGB as soon as it was launched. Within Alaska, we did a lot with nighttime microphysics, 24-hour microphysics, and daytime microphysics. Then we transitioned over to using AHI to prepare forecasters for GOES-R. So we worked with the operations proving ground to do a demonstration of how forecasters would use RGBs, how AWIPs would handle the load. And then we moved on to adapting our limb correction and intercalibration to GEO. Got involved with the GOES-R training and official quick guides. And then we did some early assessments of GOES-16 dust, daytime micro, day cloud phase, and operations. And so kind of going in today, we're still working on refining using the GEO constellation through limb correction and intercalibration, and using machine learning to improve detection and interpretation. Kind of to represent some of the work that Kevin has done, in the early days, he put a lot of work into developing quick guides. They gained momentum as an operational type of tool. We adapted them and came up with a template when we started to work with AHI and the operations proving ground. And then NOAA and the GOES-R group adopted the quick guides. We're working on some interactive RISE modules, and then current international quick guides. So it's really great to see the international adoption of these. And, one point for discussion at some point is, is everybody happy with how the quick guides are standardized and used and implemented across the globe? Okay, so here's just a very early assessment of the nighttime micro. Some things that we got out of that is that there was an impact to aviation forecast lead times. The forecasters found it very efficient. They did see some limitations with very thin or sparse fog and slowly evolving features. Out of this came forecasters requesting training that was more regionally based. We did assessment with the dust, and one of the things that we found as a big takeaway is early proxies and training for new capabilities is extremely important. 59% of forecasters benefited from using MODIS and VIIRS dust RGB prior to GOES-16, and it brought them greater awareness of dust. Again, limitations that have been noted by most people here that you're well aware of. This is a more recent assessment of the day cloud phase for lightning IDSS. There was a study by Elsenheimer and Gravel that they looked at using this RGB within Florida to aid lightning DSS, and some researchers at SPoRT widened this to the broader forecasting base. And just kind of pointing you to the bottom line is that forecasters in all regions using GOES East and GOES West with both 1 minute and 5 minute samplings were able to use and interpret the day cloud phase RGB for notional lightning DSS. Okay, so getting into some of the limb effects. We've done a lot of work to kind of help improve the air mass RGB. So at the top, you can see GOES and Severi and uncorrected, and then a corrected version. With the corrected version, you can see you do lose that contrast, but you can pick out the stratospheric intrusion a little bit closer. And then the intercalibration. Oops. So accounting for the spectral differences. The big difference is with a lot of the RGBs developed off of the Severi instrument, the 3.9 band has a much wider spectral bandwidth. So then when you start to apply the recipes that utilize the 3.9 band to newer sensors that have a very narrow bandwidth, you get different color interpretation. So the bottom diagram A is when you just apply the standard UMETSAT recipe to Himawari, and B is an intercalibration that was developed back in 2017, 2018 that we had worked on. Okay, so real quick, this is, I have a more detailed slide. How do we do the limb correction? We start with global model atmospheric profiles. We model top of atmosphere brightness temperatures. We bin the brightness temperatures. We determine our statistical relationships. So at the bottom, we have a limb correction equation for 0 to 6 degrees viewing angle. And then 60 to 80, we have a different limb correction equation that is applied. And then we have final lookup tables that are available for when we create the images to apply the limb correction and use coefficients. As far as intercalibration methodology, we need an intercalibrating to Severi. We need a proxy sensor, so we use MODIS as our proxy sensor, and we develop a brightness temperature offset based on a seasonal range of cases. And so once you apply that brightness temperature offset, you've made MODIS look like Severi, and then you can compare that proxy to each of the geostationary sensors. And so statistical relationships were done at the table in the middle there for the channels and differences that are most important for the RGBs that we're concerned with. So then we use statistical relationships to determine the new RGB recipes. So down at the bottom is an example of Severi, GO16 and GO17 and a slightly different recipe for each one. So validation, what did we do? We looked at intercomparisons. These are difference images between GO17 and GO16. And really the big takeaway is here is that when you look at these higher viewing angles, when you compare the uncorrected data, on the limb, you have brightness temperature differences between the two satellites on the order of 30 Kelvin. When you apply the limb correction, you can reduce that to under 20 Kelvin. An open mic online or something. So limb correction does reduce some of that anomalous cooling that's taking place. So here's an example of the air mass RGB. Let's see if we can click those that you can see up top uncorrected and then limb corrected. And then these are just some examples that I wanted to kind of step through. This first one is no limb correction and no intercalibration. You can see a little bit of a seam here between Severi and GO16 that there is some color differences. Those seams are a little bit more subtle with the other satellites. And then if you apply the intercalibration, you can see there's not as much of a color change that's taking place there. And then apply the limb correction. So here's kind of a table of the preliminary recipes that have been applied. So here's the nighttime microphysics just to show you, step through some examples. Again, you can see this seam right here between Severi and the other satellites. You can see more seams along the limbs when the data is uncorrected. Okay, so here's stepping through, no limb correction, no intercalibration. Here's limb correction, but intercalibration has been applied. You're gonna still see some seams close to the limbs because there's no limb correction. And then here's limb correction and intercalibration. So here's the recipes and here's the dust. No limb correction, no intercalibration. You can see how there's a little bit more consistency, and then here's both limb correction and intercalibration applied. Okay, So air mask for color vision deficiency, Katie will talk about this more, but one of the things that Katie and I did is we flipped the what's in the red component and the blue component of the air mask RGB to change the contrasting colors for forecasters that have color vision deficiency to be able to look at the stratospheric intrusion. So stratospheric intrusion is blue rather than orange. And so there's a limb corrected version of it. Differential water vapor, here's no limb correction, no intercalibration. And then here's a, limb correction. Yeah, limb correction, but no intercalibration. So you can see with this particular RGB, it does seem that you get a lot of benefit from limb correcting it. Debatable whether or not you need to intercalibrate it. And then the simple water vapor, again, no limb correction, no intercalibration. And then there's the limb correction that you would be able to utilize a lot more of that data at high viewing angles by applying that limb correction. Okay, so I'll kind of leave that summary there. So one of the things that we've been doing is we've been applying machine learning to RGBs. And so, think about some of the user questions. I always lose the dust plume at night. So machine learning could help you identify features in difficult scenes, pick up on features that we can't pick up on with the human eye. Which color or range of colors represent dust? So machine learning output could be a training or education tool. That looks like dust, but I'm not really sure. It could help to improve confidence or interpretation because you have a machine identifying what's dust and what's not. I can't use the RGB, so it could be a tool for color vision deficiency since it gives you the probability of dust. Is that a thin dust plume? It could be an aid to qualitative interpretation. So if you have the machine learning model picking up on 20% probability of dust, maybe there's a thin dust plume present. So this is, I don't want to go too deep into the weeds, but maybe just focus on our model inputs here that we use channels that are important for dust detection and differences, and also the dust RGB components. We have a paper that goes into a lot of detail on it. And we mostly just focused over the southwestern US with GO16 cases. As far as some of our 3 minutes, okay, metrics, we end up with a pretty good false positive, type 1 error, type 2 error, true positive about 85%. So there's obviously, some room for improvement, but we do pretty good with what we developed so far. So just a few examples. These are user comments. This is one case from April 7th, 8th, where the dust RGB was valued, but the machine learning output provided a longer period of time to track the dust plume. So here's the dust RGB alone, and then here is the machine learning output that's probability of dust. So what we found so far is that it's given forecasters a lot of confidence in the dust. It's helped aid their situational awareness and help them to track the dust farther into the night. So this is another event from March 2022 where forecasters were able, here's kind of a day scene, dust RGB, and here's the probabilities from the machine learning. And here's at night where it's a lot difficult to see the dust. And here's our machine learning output. So it helped aid some of their decision support. Okay, so that's it. If there's any questions.
Okay, so I promise I'll tie this all together. So Jordan asked a really interesting question earlier, which is, can RGBs become too colorful, basically? And then we've also talked about how we can mess with the recipes to some degree to have things pop. At what point do we let machine learning and AI take the reins? It's great to see that this is happening, but forecasters are stretched really thin with their time for WFOs.
Yeah, so I mean, I think it all comes down to developing the training. Whether is it something that unsupervised learning can handle, that we could throw a lot of data at it and have AI help us come up with consistent recipes or some type of tuning? I don't know. I tend to favor supervised learning. Just, you have that subject matter expert that could pick up. Maybe what somebody needs to do is look for dust in all of the, constellation of geostationary satellites, and then apply AI across the board and have it help you come up with the recipe. I don't know. The overhead to the upfront of AI can be a lot, but then it's really not that difficult to develop and implement.
I just want to continue with a comment. I really like your work on your corrections, but I have to say, from my opinion, I get confused when I see corrected products. And I just wanted to point out one thing, because I'm looking at the standard RGBs that we're using for 10, 15 years. I'm looking at this, actually staring at the same products. And I have to say that humans have a good NAI algorithm, so non-artificial intelligence, which is very good at correcting biases and making sure that we understand the scene. So I just wanted to, from the point of view of the long-term consistent use of the RGBs, I think it's fine if we don't correct too much.
No, I agree with that. I mean, it's at what point do you correct? At what point do you intercalibrate? That's kind of why I showed the simple water vapor and the differential water vapor not intercalibrated, because it looked okay. And even when you look at some of the dust and nighttime microphysics, it seems like you do need to intercalibrate that to pop out the fog. So, it's a tricky situation. As a science product, maybe a scientist who's studying stratospheric intrusions would really benefit from the limb correction of the air mass to complement their studies. But for a forecaster, maybe not so, because they're so used to interpreting it a certain way. But there's a lot that we still don't know, how many projects have we had where we've looked at strong lows and we've tried to match up the low pressure strength to the fact of whether or not there's a stratospheric intrusion there, and then the resulting color in the air mass RGB, right? We haven't taken the step to do that type of quantification to it. So do we really know always that what we're looking at is the full breadth of the stratospheric intrusion?
All right, we have Bodo online and then Marcial here in the room, and then we'll move on to the next talk. Go ahead, Bodo.
Very quickly, I think in terms of the, and I've really enjoyed this talk actually, so thank you. The interesting part I found is that the local adaptation of these RGBs, and Rion mentioned something about adapting them to the tropics. That's perhaps where machine learning could be particularly useful, because I think the forecaster needs to get an edge in, or the expert, and the machine language learning might be able just to get that start matching what you're seeing in the various tuned RGBs to what's actually observed on the surface.
We have nods of agreement in the room. Thanks, Bodo. Here's Marcial.
Just two quick comments. The quick guides, the international quick guides, you're missing Costa Rica's and Chile's.
Oh, I'm sorry.
And they're in Spanish already, so I think
Yeah.
it's pretty useful for the region as well. I'm going to show those on Thursday.
Okay, good.
And also, a few years ago, one of my students looked into extreme precipitation in Costa Rica due to a tropical storm, and he used all channels from GOES-16 by hand, comparing it to surface weather stations, and that was really painful. So I think it's great to put machine learning and AIs into this, and I'd love to see what deep learning can get out of those. Thanks.